I'm Marianne DiMaria, and we're going to learn about setting up an experiment, the variables, the procedure, and how to set up a data table. These are the regions. Lisa had these in her presentation last week. I just copied them from her, so they're there. And here's the dates of the state fair. It's a virtual fair this year, and the regional fair dates are to be determined. So this is like in a nutshell, the middle school process, the science process. I'm not, this is for like inquiry and experiments. I call like just regular experiments, like cause and effect experiments. I'm not really going through the engineering design process today, but we could do that. It's very similar, but a little different. And we can do that at another time if necessary. So today, last week, Lisa spoke about choosing a topic and setting up a notebook. And this week, we're going to do learning about variables, developing a question, developing a hypothesis, and writing your procedure. So what do we do after we choose a topic? So what I do with my kids is, this is like the flow, how I get them after they've chosen like even a broad topic. You have to figure out, you have to get them to ask a scientific question, a cause and effect question. And then after that, it's the variables, the procedure, you have to organize your data. But I'm going to focus just a little bit up front here on the safety rules, because what happens is a lot of kids like get past the topic. And if teachers aren't aware of the safety rules, then they're already down the path a little too far, and they want to do their project, but it's not going to meet our safety rules. So I put a link in here to, this is the middle school manual and forms. So what you want to do is go to the manual. If you have any questions about a kid's project, this is what I do. I just go to the manual and see. And after doing this so many years, you get to know what's acceptable and what's not. And there's a table of contents up here. And then I'm just going to go right to it. Choosing a project, the plan. And here it begins, research regulation. So may not involve at any stage of the project the following. So it's weird how there's certain things that you would think would be okay, but are not allowed. Let me see if I can give you an example. So nothing from humans. So, I'm going to take the teeth and do, how different mouthwashes affect like actual teeth. No, nothing like that. But bacteria is a big one. Middle school kids like to grow like colonies. And let's see where that is.
I think
right here. Yeah. So pathogenic agents. They're all considered potentially pathogenic and will not be allowed. And if you're going to do plants, you have to make sure that they buy sterile bagged potting soil. The other thing that I do want to point out is was somebody about to say something? Because just talk over me.
I was just going to say, sorry, it was one bacteria we do allow is from Carolina. It's E. coli K12 bacteria. But you can't still do it at home. It has to be done in a lab, or if your school has a lab. So that's the biggest thing.
Right. And yeah, if you purchase it from Carolina, that's fine. And if you do it with the students, that's all fine. But the other thing is human projects. Kids, I'm going to test, the effect of, I don't know, even reaction time projects. Like I'm going to test the effect of distractions on reaction time. And that's like a fun project to do. But humans are not reliable. That's a direct quote from one of my students like 20 years ago when I was teaching in Northborough, because like it's hard. It's difficult to use human subjects. So I try to convince all my students or guide them down the path of avoiding human projects. The other thing is there's so much paperwork involved with human projects. You have to set up an IRB, like an institutional review board at your school. And you've got to get other teachers to review projects. The kid has to have consent forms from all the students, as well as the parents have to sign it. So it becomes a lot of paperwork and adds additional layers. Now, I have allowed human projects when the student is just so passionate about the project that they stick with it, even with all of my trying to guide. And then, it really, needs a lot of guidance for human projects because of the paperwork. Everything's got to be anonymous. The teacher has to teach the student how to code, like give, you know, the test subjects a code, like M1 for male 1, F1 for female 1, etc. And the teacher keeps the paperwork so that the student's not carrying around all this paperwork. But we could talk about human subjects even in a later, I guess, workshop, because I want to get to today's topics about asking the scientific question and the variables. Okay, so the scientific question, you really want to choose one independent and dependent variable pair within that topic. So, and it should be a cause and effect question. So here are the 3 examples I'm going to use throughout this presentation. One's a chemistry project, one's a biology project, and one's a physical science project. So you can have 3 examples always to pull from. So say a kid is really interested in chemistry, right? But they can't really, they're not narrowing it down. And you learned about choosing topics last week, but one of the variables that they can do, or combinations, is how does the temperature of the water affect the rate of a chemical reaction? So independent variable here, dependent variable here. Another question they could ask is, how does the amount of salt affect the number of seeds germinated? And then another question is, how does the height of the drop affect the bounce height of a golf ball? Notice in these questions, when you're asking your scientific questions, I always try to get the kid to go into like, how does blank affect blank? And there's a reason for that. It's because the phrase right before the word affect with an A, by the way, is your independent variable. And the phrase after that, the word affect, is your dependent variable. So if you're doing experiments in your classroom and you always pose the question in this form, it really helps the kids in future experiments. Is everybody okay so far? I can't see anybody, so I'm assuming everybody's good.
Perfect.
Okay, great. So here are the definitions of the variables, but I'm not going to go through this. I'm going to go right to the first experiments, or to the experiments. So the variables, here are the examples from chemistry, biology, and physics. So for our chemistry experiment, oh, by the way, this is my go-to experiment. So these 3 experiments are all my go-to experiments for kids who are struggling, for kids who can't pick a project because they are really good with the background information. Like if our spirit is to get kids to do some really good research, take some notes, develop a hypothesis, and go through the process, then they can do that with these 3 experiments that don't cost teachers a lot of money. Doesn't take a lot of money to get the kids to do this, but you get some really nice data, nice trends if they're done correctly. And I just love these projects, these 3. So this is why I chose these 3 for this presentation. So, and this one's one of my favorites, the Alka-Seltzer project. So
I mean, Marianne, I quoted you last week with saying data is money. You always want a lot.
Data's like money. You can never have enough is what we say. And, or love, data's like love. You can never have enough, I guess, food. But, okay, so for our chemistry experiment, how does the temperature of the water affect the rate of an Alka-Seltzer the rate of a chemical reaction? Then the independent variable there is what the student or the scientist is changing on purpose. So the kid really needs to think, what am I changing on purpose? And what they're changing on purpose is the temperature of the water, okay? They're doing that on purpose. And what I tell my students is, what does it mean to be independent? Like when you're independent at home, what does that mean to you? And they always say, I can make my own choices. I can do what I want. And that's what I tell them. The independent variable is the scientist makes the choice. They're doing what they want in this experiment. So the dependent variable then is what will change in response to the water temperature changing. And when we measure the rate of a chemical reaction, we're literally measuring the time it takes for an Alka-Seltzer tablet to dissolve. So I don't have Alka-Seltzer, but I do have effervescent tablets here. So, I mean, and I don't know if you can see me. Here's a nice little picture up here, hot water versus cold water, but we will talk about that as well when we talk about the control group. So the constant variables are, if you really want to know if water temperature makes the reaction go faster, like hotter water makes it go faster and colder water makes the reaction go slower, well, you need a control, you need to keep everything the same. Everything has to be the same except for the one thing you're changing. And the only thing you're changing here is the water temperature. So some constants are the type of cup. So these are the same type of styrofoam cups, but let me go in order. The same type of Alka-Seltzer, the same size of the tablets, the same type of water. We're going to use bottled water, the same amount of water, the same size of the cups, the same type of cups. And we can go on with the constants, but identifying 3 or 4 constant variables is good. And I always make the kids put the same ... and then just list them all or bullet them underneath. Okay, the control group is interesting. There's so many different ways people define this, but the control group is not a control variable. It's a group. So what is the normal condition here? Control group is what you want to, if you really want to know if hot water or cold water affects the rate of this reaction, you better have some kind of normal condition or baseline or the condition found in nature. And what I tell my kids is like to think about that, like what's normally found in nature. And so the control group for this experiment would be the Alka-Seltzer tablets exposed to room temperature water. So we didn't make the water hot, we didn't make it cold, we didn't do anything to the water. It's just the normal condition or that found in nature. So
Marianne, I know that I'm supposed to go into chat if I have a question, but I wanted to ask
No,
you.
interrupt me anytime. Who is this, Jean or?
Jean,
go ahead.
Why are you calling it a control group versus a control variable?
Because it's a group of, it's going to be a group of tablets. So your control group is not just, it's not like, so this is where textbooks get a little crazy. So controlled variables are what they mean by constant variables, all the things that you're keeping the same. But that's very different from a control group or your experimental groups. So I like to get rid of the word, like students always think controlled variables and they think that's what their constants are. The control group is the group that you're going to use as your baseline to compare the experimental data to. It's kind of like, you know how you have a control group for drug testing? Yes.
But what if you do call it a control variable?
I think you're okay, just as long as the kids know, right?
Yeah, I do teach it not as a control group, but a control variable. And so what do we want to control? And it's the water in this case, and it would be the temperature. So what control variable do we want to use? 20 degrees Celsius, you know, so that they can pick that out. But it wouldn't be wrong to call it a variable because I've had done that all the time, you know.
No,
so
that's fine. I like the word group just because like it's a group of tablets, like say, because you're going to have to repeat this many times. So if you do 20 trials of each, like the room temperature, the hot and the cold, then your control group is the 20 tablets that just got room temperature. So it's like a group, like a little group, or it's your control group would be the group of plants that just got room temperature water. Okay. Because you wouldn't just use one plant, right? You wouldn't just use one Alka-Seltzer tablet. If it, like, not now, but in the future, I would switch over the vocabulary like this so that you can just get away, like separate the controlled variables and leave those as constants. But I agree, it's very confusing.
Well, yeah, I know the constants are easy. They can pick that up. It's the control group. I mean, like I say, the dependent variable. What are we trying to measure here? There's your dependent variable. Dependent is always measure.
Well, see, this is where like you'll get the kids who, but I measure the water temperature. I measure other things, and that's true. They're right. So I used to do, Jean, I was like, would say the dependent variable is what we measure to get the answer, because you measure so many things in an experiment. So let me go back to that definition. So let me go back to the definition. So I love this. I love this conversation. Thank you for asking these questions. So the independent variable is what the scientist changes on purpose. And then the variable, the dependent, is what changes in response to the independent variable. You hope that you have some differences in your groups. So constants we all know. So here's how we define the control group: is this group does not get exposed to the independent variable, or it is the group that is used to compare to. It is the group most representative of what is found in nature. So this isn't really a variable. It's not something that you're changing on purpose. This is a group of things. In our case now, it's a group of Alka-Seltzer tablets. And it's easier if we talk about the experimental groups. Then are the Alka-Seltzer tablets exposed to cold water and hot water. So you've got 40 more tablets, a group of 20 that is getting just exposed to cold water, and a group of 20 that's just getting exposed to hot water. Does that make sense?
Oh, it makes sense to me. I'm just trying to think of it as simple for terminology for students that, you know, because in my situation, they all have to do it. It's everybody does a scientific method project of some sort. Of course, you're better students. I kind of work with them on the side, but so I try to make it easy for them, and because they get the independent variable, the things I'm going to test in this problem statement, in this hypothesis. Like the hypothesis for me, I teach, if I do this, then this will happen. That's my basis on actually writing a hypothesis.
Yeah, I didn't put that slide in. I guess I should do that, but I could put the hypothesis right there. So let's write that together. And I would write it like, so Jean, tell me for this experiment, right? So we all have, I'm putting you on the spot, Jean, but that's okay. So we all know about basic chemistry. This experiment, the background that I would have a kid do is collision theory. So as you know, what is temperature? Temperature is the average kinetic energy of a system. So as water molecules are moving faster and faster, the temperature goes up and up, because, you know, that's more energy, okay? So if these molecules are moving faster and faster, then the water molecules, if they're hotter, are going to bump into your tablet more, and literally, I don't know if you can see the tablet, literally collide and bang on it so that it might dissolve faster. So let's write that in an if-then statement. So go ahead, Jean.
I would say, see, what I try to have them do is, what is it that they're trying to solve in the statement, in their problem statement?
Yeah.
Right. So what effect does water have on the rate of Alka-Seltzer, whatever?
Yeah.
So I'm using, so if I use, what's your independent water temperature? If I use water temperature at 30 degrees Celsius, 40 degrees Celsius, 50 degrees Celsius, then the 50 degrees Celsius will cause the Alka-Seltzer to change faster or dissolve quicker or something. I don't like to use the word quicker. I don't like anything that's not scientific. Okay. So it's like, if I do this, then this will happen, and then have them fill that in.
I have an easier method. This is the
first time I've seen control group, and I'm interested in it. So this is good.
An easier method would be, because it's not a race. It's not like kids always say, like, this one's going to be first, then this, then the. It's try to get them to switch to predicting a trend. So the way I would have my students do this was, if the temperature of the water increases, then the rate of the chemical reaction is expected, because it's a hypothesis, to, now what would you say to that? If the temperature of the water increases, what would you expect to happen to the rate of the reaction? Would that increase or decrease?
Yeah.
Increase. So at the hotter the water, the faster the reaction is going to go. And I'll add these slides in. Karen, Helen, could I add the slides in later to this presentation or no?
Absolutely. Yep, absolutely.
Okay. So that's how I would have them state the hypothesis for this. Like if the temperature of the water increases, then the rate of the chemical reaction is also expected to increase. Because, and then they would say, this is expected because of collision theory. And they would go on and explain collision theory in one good real paragraph. Like
right. Or if you didn't give them any background and they watched and observed and they could see, well, the molecules are moving faster. What is that? So it's after the experiment that we begin to take it apart scientifically.
Right. And then say, and the most interesting results are when things contradict your hypothesis. And then you get to really break it down and go back to the literature and say, well, let's do some more research because we clearly, both of us were expecting something different and that's not what happened. So I agree with you, breaking it down afterwards. But I will tell you, the reason why this is my go-to with certain students, like students who need some more support, is because this always gives amazing data, really good. If I can share some data next week, maybe, or with Helen and Karen, I've actually have the actual data from several students' projects. So I can do that.
Okay.
I was going to say something else. Oh, there's a reason why I don't have kids say, if the temperature of the water is 40 degrees Celsius, because what if it was 38 degrees Celsius? What if it was 37 degrees Celsius? What if it was like 5 degrees Celsius? So that's why I always have kids predict the trend rather than go with just the 3 temperatures we're using. Like, so like 60 degrees, it's still gonna work, you know what I mean?
Right, but what they end up doing is getting the temperature to be that. And then you realize that the temperature is changing even once you get to a certain, you know, so that eventually comes out.
And another suggestion, I've had kids do this, like ideally, obviously the kids who do this with me are the kids who need a lot of support. So they're in the lab with me and we're using glass. We're using glass beakers, flasks. Yeah. So, and obviously goggles, safety goggles, but I've had kids use plastic cups and they melted really even with the 40. So styrofoam is highly recommended for this experiment. And you can also use, so hang on, let's go forward now. I'm actually going to continue with the chemistry one. So I've got to go all the way to the end. I've got to show you something. So for everybody on here, Helen and Karen, I don't know if this is okay, but I'm going to click on this. Okay. So 20 years ago, when I was in Northborough, the social studies teachers and the science teachers together wrote a research handbook. And this is 20 some years late. It was 55 pages long. It was overwhelming for kids. But I have spent 20 years modifying this. And this is the current version. And is it okay that I link this, Helen and Karen?
Yeah, absolutely. If there's anything you want to take out of it, but Lisa linked.
No, this is a copy, and this was for this year. This is what I'm going to be using for this year. And so it just starts, and there's a table of contents, and it's 30 some pages. But where we are is like I broke the whole science project down into this isn't for this year because I didn't change the dates. This was last year's one. So you're seeing last year's. But I broke the whole project down into 10 homework assignments. But I really do, and there's a bunch of examples in here, but I'm just showing you where we start. That's choosing a topic. I do want to point out when we do research, I send my kids to these websites first. If it's a chemistry project, they go to Chem for Kids. Biology goes here, and it's like a great bit like start to get them to build a base of knowledge. Like if you look at research like that pyramid shape, but I want to go to page, I think it's here. I should know. Step 5, materials and methods. So these questions are in this guide, like how many levels of your independent variable will you test? How will you measure your dependent variable? What is your control? what are your constant variables? And the kids fill out this piece right here. They do it in their lab notebooks, even though this guide looks like it's a fill in the blank kind of guide. So I'm going back here now. Oops.
Jeez, Marianne, you should put this on like Teachers Pay Teachers here for that, that guidebook.
You know, you think so, but I've given it away so many times. So, you know, that's fine by me. So again, when the kid is developing, so once they've identified the variables, a lot of times it's a lot easier to like bring out all the supplies and have them in front of them and like try to do the experiment once before you identify your variables, and try to do it once, because that will help when you're actually writing the procedure. So I make the kids in their notebook, they actually have to answer these questions. So we're going to do how many levels of the independent variable? We're going to do 3. The 3 levels are cold water, hot water, and room temperature water. And going back to Jean, these are your 3 groups, by the way. Okay, so how will these levels be created? They need to specifically tell you, like I'm going to get hot water out of the tap. I'm going to get cold water out of the tap. What are you going to do with room temperature water out of the tap? So literally they have to think, okay, I have to fill 3 1-liter containers with tap water, leave 1 at room temperature, heat 1 to 40 degrees Celsius using a heating block, and place the final liter in the refrigerator. Okay. How exactly are you measuring the dependent variable? So how is the rate of the reaction going to be measured? And so that they're going to use a stopwatch on a cell phone and wait for the tablet to completely dissolve. And by the way, that's even a problem. Like, is it dissolved now? You know, like you're looking in the container.
Fusion, yeah.
Yeah, and then I have them fill out this. We already went through constants and the Alka-Seltzer tablets. So there's a lot of repetition here, but it makes them really think. Okay, what are your materials? This is important too. Like, what do you need to get this going? But here's now the procedure. So I start with the same thing here. I just want to, you can read through this on your own. Use the thermometer to measure the exact temperature of the water. Pour 150, get the stopwatch ready. But the key here is repeat. So try to get them to use like they don't have to rewrite like everything for the cold water. And then, so it says repeat steps 3 to 8 with the cold water. Be sure to leave the container of cold water in the refrigerator between trials. Repeat steps 3 to 8 with the hot water. And then the last thing is repeat steps 3 to 10 4 more times until you have completed 5 trials for each water temperature. Honestly, I make my kids collect 100 pieces of data. So they're not doing this just 5 times each. They're going to do it 33 times each so that they get 99, data points, and then, take the average. And that's why it's really important with an experiment like this. You do like room temperature. Oh, look at error. Hot, cold, like this is cold over here. I found an error in my data table. That's so right. They do room temperature, hot, cold, and then do that again. They can't do like all the room temperature one day, all the hot one day, and all the cold, because there could be minor differences in your room, like minor temperature differences or whatever.
Yeah, but you do take the temperature of the water, so you know what you're working with.
That's right. And 4 degrees.
What's cold water?
Yeah.
What's hot water? I mean, I always have a thermometer. I said, we're doing anything with temperature, find out what the temperature is for whatever you're testing. Yes.
So find heat I think it says temperature somewhere, the thermometer somewhere, but the refrigerator is 4 degrees. That's what refrigeration is. And our room temperature at my school is around 20, sometimes 21 degrees Celsius. So that's why I randomly picked that. So hot, 40 degrees, even like 30 degrees Celsius is hot enough to see the differences here. And this is my classic data table too, with the independent variable going across the top, the trials going down the side here in this column, and then always the average at the bottom. And then the tables are always labeled, this time effect with an E, effect of temperature on rate of Alka-Seltzer chemical reaction. So it's always that independent variable, dependent variable combination coming up in titles and in like your scientific question. Questions here on the chemistry one. Do we have time? Do we have time? We have time, right, to go through more? Is that good?
Yeah, usually I say they're like 30 to 45 minutes. So if you want to go through another one, go for it.
Jean, or I forgot, who was the
Bethany.
Bethany. I was going to say Betty. Bethany, any more questions there on this chemistry one? So let's.
No, I'm good. Thank you.
Thanks. So let's go through the process again with the bio. So this is an experiment I actually do with my 7th graders in like for abiotic, biotic factors and ecosystems. I think that's one of our standards. So it's pretty easy. So in this question, let's go back to the questions. Where's that question? How does amount of salt affect the number of seeds germinated? And really it should be, how does the amount of salt in a solution affect the number of seeds germinated? So what the kids do is, you know, what are they changing on purpose? The amount of salt in the solution. They literally count the number of germinated seeds in the Petri dish. The constants are the same: type of salt, amount of water, type of water, type of Petri dish, I guess we could say. Like I have some Petri dishes here. And temperature. This time temperature is kept constant. It's just going to be room temperature. So Jean, let's have that same discussion about the control group now. So what's the control group here? It's the seeds exposed to 0% salt or just water only. Okay, no, like, so what's found in nature out there? How do seeds germinate? Normally it's just rainwater, and rainwater should just be pure water. So that's the logic here. So all the seeds that we expose to just water are our control group. And then we have 4 experimental groups here. Seeds exposed to these levels of salt. Any questions here with this one?
Why do you have percent, 0.5%, or do you measure it in grams or at all?
Yeah, so percentages are easy for the kids because like they know their grades, like they know 100% on a test is 100. So when I say we're going to make a 1% salt solution, I say like that would be 1 gram in how many milliliters of water. So
you don't necessarily use the word gram.
No, we use the word gram. We measure in grams.
Okay. All
yeah.
Right.
So honestly, I just went through this with my 10th graders too. For me, my brain works easier. Like I do, like when I do solutions, like I do molarity as well, because I teach chemistry, but sometimes, but it's easy for us to do percentages because it's literally 1 gram and bring the volume to 100 milliliters. So it's easy for me with a 1% solution. Then I know, well, if that's 1 gram in 100 milliliters, then I only have to put half a gram in 100 milliliters or 1.5 and bring the volume to 100. So it's just easy math. Just makes the math easy for me and them. Is that good?
Yeah, that's good. I mean,
but you can do whatever you want. Like,
no, that's good. I see that. I think.
Yeah. Science Buddies, like Science Buddies has a lot of really good experiments, but a lot of times they use like kitchen chemistry, which is good too. Like put a tablespoon, like 1 tablespoon, 2 tablespoons. You could do that. This project would work.
I have them converted.
I just know, I know like, because I've done this so often with kids, I know like at 0%, all the seeds will germinate here. At 2% salt, you won't get anything germinated. So if you overshoot it right away, you're not going to see that nice trend. So let's state the hypothesis again. We do like some research with the salt. Like I actually cut up eggplant and pour salt on it, and the salt draws all of the water out of the eggplant. So they see that in the classroom. And I'm like, okay, so does salt attract water or does it not attract water? And they're like, it attracts the water. I'm like, okay, do seeds need water to germinate? And they do some research on that. And they're like, yeah, it's got to soften the seed coat. It's got to get the, chemical reactions inside the baby plant going to start it growing so it could pop out. So I'm like, okay, so if the salt is pulling all the water, do the seeds, does that baby plant get the water? And they're like, no, it's kind of like a tug of war. So if we were going to state a hypothesis for this experiment, how would we state it? Using the trend again. If the amount of salt increases, right, then what would you expect to happen to the number of germinated seeds?
The seeds, less seeds will germinate, if at all.
Excellent. So if the amount of salt in the solution increases, comma, then the number of germinated seeds is expected to decrease. So what you're predicting here is, like, with 0%, you're going to get the most germination, and then less and less and less. I'm pointing to the things as if you can see me with my finger. So most germination here, and then less and less and less and less. And we actually saw that trend this year because I adjusted the salt concentration so that we got 100% germination here, 0 here, and then these 3 fell in between. We actually, like, this was like 8 out of 10 seeds. And it was repeated many times. So that's like an average. I can show you the data from that experiment too. And so going now to that experiment. So this time there's 5 levels of the independent variable. These are the levels. These are your salt solutions. And then how will they be created? And so I literally say mass that amount of salt and add to 5 separate containers, add 100 milliliters of distilled water to each container and stir until the salt completely dissolves. Now that's not perfect because you're supposed to, add it and then bring the volume up to 100 milliliters in a graduated cylinder. But this is good. And, this is good for the salt really doesn't displace that much water. How exactly will the dependent variable be measured? Okay, so you're going to count the number of germinated mung bean seeds in each Petri dish, and germinated seeds will be those seeds with a small root growing out through the seed coat, because that's always a question, like, when has it germinated? Does it mean it just broke the seed coat? Or no, we're saying you have to see that little root. You have to see, so I think there's a picture over here. You have to see these radicals coming out. If you don't, then it has not germinated yet. And then you're going to calculate the percentage of seeds germinated. And so that's a little spin on the dependent variable there that I added in. And then what are the constant variables? We already went through that, and we already know control group and your experimental groups. You have 4 experimental groups this time. And then this is so simple. All you need are Petri dishes and paper towels, but there's also these little foam things. You can put them in the bottom, like these kinds of things. And we put 10 seeds in each dish. And then you need at least, this one you do need distilled water, because you don't want to use tap water just in case there's anything in there. Paper towels could be cut up to put into the bottom of the Petri dishes. And then you need salt, just regular table salt will do. And then this is a really quick procedure. You just place the 10 seeds in, add about 15 milliliters of the 0% salt solution on top of the seeds in the dish labeled 0% salt. Cover the dish with the lid, but angle it so that you let some air in, but you don't want your liquid to all evaporate. And then repeat steps 4 to 5 with the other salt solutions and count the number of germinated seeds in each dish every day. You could do it for 5 days and record data in the lab notebook. Now, this one is a little weird because if you're going to collect, data, so notice how I set up the data table here. Percentage of seeds germinated only on day 5. The reality is they really germinate by day 3 or 4. You're going to get your answer here, most of the germination experiments. And so in this one, you're going to have, the kid's going to have like hundreds of data points in their lab notebook, but really we only need the data from day 5 to get the answer to the question. But I would repeat the experiment again and again and again for 5 times. And then you get like 25 data points here, but in reality, if the kid was looking at them on day 1, day 2, day 3, they have a lot more data in their notebook. Questions with this one?
Marianne, I had a quick question.
Yeah.
So you're doing 10 seeds per, 0%, 5%, 1.
Yeah.
And then you repeat it 5 more times for each one. Okay.
Yeah, but not at all at the same time, because so you want to do, thanks, Karen. You want to do the whole experiment. You want the kid to do the whole experiment, let's say once, and it'll take 3 to 4 days from start to finish. But say nothing happens. Say, like, you don't want kids setting up all 5 trials all at the same time, because if you have a problem with your salt solutions, or maybe there's a problem with the seeds, you just spent a lot of time for nothing, and kids sometimes do that. How many of you, like, have you had like kids collect 100 pieces of like 0 data, and you're like, wait, like you should have like revised your procedure early on. You have an error somewhere here. Something's not right. So you want to make sure you do it once, like going across this way, and then wash out those dishes and set it up again. If your salt solutions are working well, you can use them. Like I wouldn't make a ton of salt solutions right at the beginning. I would just make the 100 milliliters of each, and then make them again, and then set it up again. Does that make sense? Hello?
Yeah, that's great. We were shaking our heads. Sorry.
I'm sorry. I can't see anybody.
Oh,
sorry.
Okay.
Okay.
Sorry. We were shaking.
I'm so sorry.
You only test one variable at a time anyway. So if it's a set, whatever. So that's important. Just do
absolutely. Yeah. And so let me go back to the scientific question. I forgot to tell you this early on, and I didn't make a slide. So even going back to the chemistry question, where is the chemistry one? Right here. See, so one of my students a long time ago defined constant variables. Did I put that in here? Here. So Mrs. D, they're the changes that don't change. And I thought that was the most brilliant definition of constant variables, because I tell the kids, what does constant mean? The same. What does variable mean? They go like to change. I'm like, okay, so what, that makes no sense, right? And so one kid said, yes, Mrs. D, it's the changes that we don't change. And I'm like, okay, that's great. So they could be changed, but we choose not to change them in this one experiment. So Jean, you reminded me, thank you. Each one of these could become a different experiment. So you could ask, how does the type of water affect the rate of the chemical reaction? How does the amount of water affect the rate of the chemical reaction? How does the size of the tablet? There is a Science Buddy project where they crack the tablets like in half and in quarters and then crush them. And obviously the smaller the surface area, the faster the reaction, because the water molecules can get there faster. Each one of these can become a different cause and effect question. So if the kid's struggling with the question that they're asking, you might want to look to their constant variables and say, well, maybe we should switch it a little bit. And the same thing here with the biology one. You could ask, how does the type of salt affect the the percentage of seeds that germinated? How does the amount of water, how does the type of water, type of seeds, etc. Each one of these can become a whole other experiment. That makes sense, right? Mm-hmm. Okay. Finally, another one. This one is, there's so many versions of this. I just picked a really easy one. That, how does the drop height affect the bounce height of the golf ball? Okay, well, I don't have a golf ball here, but I have a different type of ball, and I'll show you why. So what are we changing on purpose? The height of the drop. What are we measuring, or what should change in response? The height, the bounce height. And this is like potential kinetic energy at its best. Okay, it's like the classic, and that is a 7th grade standard, by the way. So we're hitting a lot of things when we do this. So what do you have to keep the same? It's got to be the same type of golf ball, the same meter sticks, the same temperature, the same type of floor that you're bouncing off of. And that's pretty it. Simple. This one is simple. Now, Jean, here's where our conversation about the control group, these kinds of experiments, like what's found in nature, I don't know. I don't know what drop height is found in nature for golf balls. In this one, I encourage kids to choose one of the ends, either your lowest drop height or your highest drop height. So for this experiment, I chose the 125 centimeter group, like all the balls dropped at 125 centimeters. That's going to be our control group. Okay. Then notice how the drop heights get lower and lower for my experimental groups. So if we were going to state a hypothesis for this one, it would be if the drop height decreased, we'll go in the order that I have here, then the bounce height, what would we predict for the bounce height? So if we're decreasing the drop height, what should happen to the bounce height? Will that also be expected to decrease as we go this way? Or would it be expected to increase as we go lower and lower?
Would decrease.
That's right. Thank you. If the drop height, drop height decrease, then the bounce height is expected, I'm writing this down, to also decrease. And then you'd explain, because the higher the drop height, the more potential energy, etc. So, okay. But this is a good one. And I love this one because it really, it's not exactly perfect with control group and experimental groups. Karen, do you agree there with what I'm saying with these kinds of experiments when you don't have like that pure control group, what's found in nature, or the one not getting the independent variable, etc.?
Yes, yes.
Yeah, because kids will say like the control group would be no drop height, zero, like you're not going to drop it off the floor, like from 0 centimeters, right? That's not like, so potentially you could leave the ball on the floor and then say, okay, the bounce height is 0, 0, 0, but that's not exactly what we do. Okay, so now here are the, for the physics experiment, we're going to do 5 drop heights, so 5 levels. Okay, how will these levels be created? So we're going to tape 2.6 meters. Imagine 2.6 meters back there. Tape, literally encourage the kids. They have to tell you, like they're going to be taped to the wall end to end to create a 200 centimeter ruler. Place the golf ball in the dropping tool and align the bottom of the golf ball with each drop height and pull the trapdoor. Now I had to show you this because my kids and I, a couple of years ago, there's so many versions of this. So, and you need to, like, kids need to think you're going to need 2 people for this experiment if you don't want to videotape. And the first person has to drop the ball and the second person has to mark. And are you going to mark it where the bottom of the ball goes to or where the top of the ball goes to, like on the meter sticks? So I don't know. Can you guys see this? This is like a typical dropping tool. So this is my coffee, like just a coffee container from my Nespresso, and I cut slots in it. And this is just a slide. And I created, and I couldn't find my golf ball didn't fit. So I have just a regular bouncy ball. And when the kid like goes to line this up at, let's say 125 centimeters, Karen, can you see me?
Yes, we can. Yes.
Okay. Then you don't want, the kid can't just drop it because they could apply some force and like not realize it. So this is where you keep everything constant. You just want to pull the trapdoor and there it goes. And I lost my ball. So these trapdoor things can be made out of anything. We've had kids bounce tennis balls because kids, like, if they're interested in tennis, like that whole thing, if you watch the French Open recently, which I love tennis, like Nadal was complaining because it was so cold because they just played it recently in the fall. And normally that's played in the spring and it's sweltering hot in France. So the balls bounce differently. So we've done it. We've taken the tennis ball containers and cut slits in it and we just use a ruler. It works with anything, but like just making some dropping contraption is also really good because the kid has to think of, oh, you know, I didn't realize I have to actually keep that constant too. So this we all know. So literally, I just wrote this like exactly what, like in as much detail as possible so that anybody can repeat this. Make sense?
Yeah,
and notice this one repeats steps 3 to 8, 25 times for each drop height. So 20, 25 times. This one, this does not have a lot of setup. It doesn't like require a lot of time. Like the kid drops and it bounces, drops. So this kind of experiment, I would expect hundreds of pieces of data. Because the spirit of the science fair to me and the projects is long, like you're not going to collect all your data in one afternoon. Like it really should be like at least a week or two of, you know, collecting data over that period of time. Maybe not every day, but definitely, you know, and like tweaking your procedure if things aren't working. And then here's the same thing. So here's the bounce height, again, independent variables going across the top. And then this would be like 20, 25 times going down and then just average. Oh, that's it.
That was awesome, Marianne. That was really
excellent. That was very helpful. Yeah, very helpful.
Thank you. I just want to, so next week is the November 18th. No.
Yes, November.
It is November 18th.
Yes.
Analyzing data and writing a conclusion. I'm going to get back to I just want to see. Okay, so in that project handbook, there are a ton of links. Hopefully all the links are working, but feel free to use anything on there, okay? And then that's my email. So any other questions? Could I stop sharing my screen so I can actually see people?
Yes, you can. And I will, Marianne shared this presentation with me, so I will share it with you all. I shared today's with you, or last week's with everyone. So we will have that. And yeah, this was awesome, Marianne. I mean, if you're interested, do you want to do next week's also and show us how, you know, the data, how you analyze the data and everything from these experiments?
I would love to do next week's because I have real data from definitely the first and second experiments. And I have versions of the third one, the physics ones, with not with this, but with like the actual tennis ball data. I can find that. So I could put that together really quickly.
Good. Okay. Marianne, this was excellent. How soon will the slide presentation be available?
I will get it out to you guys later today just to make sure it either today or tomorrow morning. I'll just make sure all the links work and stuff from my end.
And feel free to use the handbook. Just caution, those dates don't match up. Like I have to redo the dates, but feel free to use whatever because it's and to chop it up, cut it up like I don't, by the way, that handbook, I don't just hand to kids. I dole it out in sections because if you hand them a 30-some page document, they'll flip out right away. And at the end are your, the Mscf grading criteria. All of my grading criteria are like stolen from like the judging criteria on our website on the, you know, Worcester regional, like what used to be there, Karen. So it's all of, and I think I say that like adapted from. It's really not adapted. It's like totally stolen. I think I'm still being recorded.
That's okay.
Okay.
We do it. All right. Well, if you guys don't have any other questions, I know this was awesome. I won't keep any more time of you. Sorry. They've been jumping on a bed the whole time.
They're so cute.
So you probably saw my side eye. But Marianne, thank you so much. And Bethany and Jean, thank you so much for coming. And like I said, I will send this out to you guys.
And feel free to email if you have any more questions.
Yes.
Thank you. Thank you.
We will be posting it on our website once we upload the video and everything like that. So perfect.
Thanks.
Well, thank you guys. I will let everyone go. Marianne, if you want to stay on a sec, you can.
Okay.
All right. Thanks, Bethany and Jean.
Bye. Bye, Bethany. Bye, Jean.
Thank you.
You're welcome.
You're welcome. Karen, can I share my screen one more time?
Hold on, let me stop recording. Stop recording.